So now that we have analyzed a fluid at rest, let us proceed to analyze a fluid under motion. So fluid under motion can, the stress for a fluid under motion can be represented as this. The minus P delta Ej still remains from the static part and an additional sigma Ej. So this particular component is called as the static component. This component is called as the deviatoric component. So this is the deviatoric stress. Now the deviatoric stress, we have seen that it depends on the rate of strain. So sigma Ij is dependent somehow on the rate of strain tensor. And I'm not writing Ij because it can depend on other components of the rate of strain tensor also. And once again, because the fluid is under motion, P that we write over here, it is not exactly the equilibrium pressure, but it is in a certain approximation where the fluid relaxes very quickly. So what do you mean by relaxation? That given a disturbance from equilibrium, the fluid is able to reach equilibrium very quickly. That if you run a flight of steps, how fast can you sit down and calm down yourself so that a person who sees you can say, okay, he did not do anything, he is in equilibrium. If you are not in equilibrium, you will keep on panting for 5 minutes, but if you are in equilibrium, you will seem like you have not done anything. So if the fluid is able to reach equilibrium very quickly, this P can be approximated as the thermodynamic pressure or the equilibrium pressure. But the deviatoric stress is represented in terms of the rate of strain tensor, and a way to relate a tensor with another tensor is by means of a fourth order tensor. So a fourth order tensor is something which maps a second order tensor, in this case the rate of strain tensor, onto a stress tensor, much in the way like a vector can be mapped into another vector with the help of a second order tensor. Okay, so fourth order tensor mapping requires this. Now let us look at the different requirements of this relationship. Okay, so for this relationship to hold true, how many variables we must have? So I can go from 1 to 3, j can go from 1 to 3, m can go from 1 to 3, n can go from 1 to 3. Meaning sigma 11 is a function of S11, S12, S13, dot, 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 all the way to S33. So this relationship between all these terms in a linear fashion can be done by means of 81 constants. So sigma 12 will also be some function of this, sigma 13. Okay, so this relationship that we can write will involve 81 constants, but that's really cumbersome to do. So we must find out various underlying symmetries in the problem which can help us to simplify the expression for the stress tensor. So the first requirement is that the stress tensor must be isotropic. If the stress tensor is isotropic, then the fourth order tensor which maps this rate of strain tensor must also be isotropic, meaning Kij Mn must also be isotropic. And the only way to express a fourth order tensor through isotropic means is by using two Kronecker deltas, rather a pair of Kronecker deltas. Now the requirement of the tensor being symmetric means you can swap I and j and still obtain the same result. So ij should be swappable. So if it is swappable, it means that k j I m n will be lambda delta ji delta mn plus mu delta jm delta in plus gamma delta jn delta in. And because it is equal, so k jimn is also equal to k ijmn, and it is equal to this thing. Now ij are swappable for delta because I equal to j is all that matters for the Kronecker delta. So this will be delta ij delta mn. This mu from this equation and gamma from this equation, these two terms exactly match. Delta in delta jm delta jm, delta jn also match. So these two terms are also equivalent. So I'm not going to write it down, but the condition of symmetric stress tensor implies that mu equal to gamma. Thus kijmn so far is lambda delta ij delta mn plus 2 mu delta im delta jn. So with this we can write down the deviatoric part of the stress tensor as kijmn smn. This is lambda delta ij delta mn smn plus 2 mu delta im delta jn smn. Now delta mn smn is going to be non-zero only when m equal to n. So this becomes smm, and this is simply 2 mu delta im delta jn smm. Now what is smm? SMM is S11 plus S12 plus S13, rather S22 plus S33, and this is nothing but the trace of the rate of strain tensor. And the trace of the rate of strain tensor, you may recall, is nothing but the divergence of the velocity field. Alright, in that case, we can write this as sigma ij is equal to lambda delta ij divergence of velocity plus 2 mu delta im delta jn smn. So the entire stress tensor may be written as minus p delta ij plus 2 mu delta im delta jn. In fact, let us simplify this delta im delta jm also. So only when m equal to I and only when n equal to j, this term will be non-zero. So this becomes, so replace m by I and n by j. So this becomes Sij. So already we are able to recover the kind of form that we are used to. This is 2 mu Sij. For unidirectional flow, this boils down to the Newton's law of viscosity. You should be able to verify that. Newton's law of viscosity for unidirectional flow. Now, when we set I equal to j in this expression, this becomes tau ii is equal to minus p delta ii. Now, delta ii is equal to delta 11 plus delta 22 plus delta 33. It is equal to 3. So, this becomes minus thrice pressure. This becomes minus 2 mu Sii plus this becomes again 3 lambda, the divergence of the velocity. Moreover, Sii once again is the trace of the rate of strain tensor, and this becomes minus 3p plus 2 mu plus 3 lambda times the divergence of the velocity. Now, divergence of velocity, the diagonal components need not be equal, unlike this. So we can simply take an average. Okay, we can simply take an average and define the mean pressure, define the trace of the stress tensor as the mean pressure. So the mean pressure equal to trace divided by 3. Essentially, this is by definition. So this is equal to minus P is equal to tau II, the trace of it divided by 3. Essentially, it's like taking an average of the diagonal components. So if this is true, we can write down this expression as minus 3P bar is equal to minus 3P plus 2 mu plus 3 lambda times the divergence of the velocity. And the reason I am writing it as 3P bar is to differentiate this pressure from this pressure. This is the thermodynamic pressure. While this is the mechanical pressure. It is the mechanical pressure because it is the trace of the stress tensor. Alright. So now in that case, we can finally write down P minus P bar. So let me take this over here. We can write it as 2 by 3 mu plus lambda times the divergence of the velocity. So the difference between the mechanical pressure and thermodynamic pressure is manifested by means of this particular coefficient, which is called as the bulk viscosity. And the bulk viscosity is a measure of the compressibility. So if the compressibility is equal to 0, that is the flow is incompressible, then the mechanical pressure and the thermodynamic pressure become equal. When the when the flow is compressible, this will not be equal to 0, and the deviation between the mechanical pressure and thermodynamic pressure will be manifested through the bulk viscosity multiplying the degree of compressibility of the flow. It is not the compressibility of the fluid, but it is rather the compressibility of the flow. The more the flow will be compressible, the more important this bulk viscosity will be in the calculations. And this is typically important for problems of acoustics, problems of compressible flows, shock flows, and so on. But for typical flows, if the flow is divergence free, the bulk viscosity does not come into the picture. The Stokes hypothesis says that 2 by 3 mu plus lambda is equal to 0, meaning the bulk viscosity is 0. And in fact, it is 0 for most monoatomic gases and all those things, but for polyatomic gases, this is actually non-zero. Because it is that microscopic detail of being polyatomic that imparts a certain compressiveness when the flow of such fluids does happen. So now, what have we inferred so far? We know that tau ij is minus P delta ij plus 2 mu Sij plus lambda times the divergence of the velocity. We can substitute the, the pressure from the previous terms over here, but in fact in this particular course, because it's a basic level course, we're gonna consider incompressible flows. This term vanishes, in which case the stress tensor is going to be minus P delta Ij plus 2 mu Sij. This is the form of this stress tensor. Now when we take a divergence of this, essentially the right hand side of the Cauchy momentum equation, the first term will give minus del P del Xj, while the second term will give del Xi of 2 mu Sij. So Sij is half del Uy del Xj plus del Uj del Xi. So this becomes minus grad P, its J component plus, so this 2 cancels out, so it's mu del 2 ui by del xi del xj plus mu del 2 uj by del xi 2. Now if we focus on this del 2 ui del xi del xj is nothing but del xj of the divergence of the velocity, and if the flow is incompressible, this again vanishes. So the divergence of the stress gives us the gradient of pressure, its j component, plus mu Laplacian of the j component of velocity. So essentially rho d uj dt is equal to minus gradient of p, its j component, plus mu Laplacian of the j component of velocity plus rho gj. In a vector form, this may be written as rho du dt is equal to minus gradient of pressure plus mu Laplacian of u plus rho g vector. Now let us take a step forward and simplify this, because it's a Laplace operator and a velocity. We can make use of the vector identity that the curl of a vector is equal to the gradient of the divergence of the vector minus Laplacian of the vector. This is a vector identity. You can easily prove this using the index notation. And I request you to go ahead and prove this in your leisure time. It is a good exercise to do. Just remember that the curl of something epsilon ijk. So the I component of this curl will be epsilon ijk del xj ak. So you have to make use of this form, and everything else is self-explanatory. Using this, if the flow is incompressible, this vanishes. So this becomes equal to minus of the Laplacian of u. So this particular equation may be simplified as rho du dt is equal to minus gradient of pressure. So now using this identity, so curl of the velocity will be vorticity. So this term becomes minus mu curl of the vorticity plus rho g. And so essentially we have an equation in which the force is somehow dependent on the vorticity, but we have already discussed this in one of the earlier classes that the forces must not depend on the vorticity. But why does vorticity appear over here? In fact, it actually does not. The stress does not depend on the vorticity, it depends on the rate of strain, rate of deformation. But the reason why vorticity appears here is it is the curl of the vorticity. It is not the vorticity alone, but the way vorticity varies spatially that gives rise to viscous stresses. If vorticity is constant in the flow, meaning there is some sort of solid body rotation, then this term automatically vanishes. When viscosity is negligible, rather viscosity is absent. I mean, viscosity can never be absent. Speaking for common examples, of course, I'm not talking about superfluidity and all that. So when viscosity is zero or when viscosity is neglected, then the equation boils down. The Cauchy equation becomes this in an inertial frame. This particular equation is called as the Euler equation. Now we can sort of we could have derived this Euler equation from a different viewpoint also. We can derive the Euler equation from simple momentum conservation principles. Let us consider a streamline on which there is a fluid element. Let this direction be S, the streamwise direction, and this direction be N, the normal direction. So the acceleration, so we know that the fluid element will move along the streamline. So the velocity is always going to be along the direction ES as opposed to the direction EN. But the acceleration will have both components. So the acceleration in the S direction will be del V del T, where V is the magnitude of velocity in the ES direction. So the velocity vector for this kind of flow is simply VES. So it will be del V del T plus V del S of V. But what are the forces acting on the fluid element? It is the pressure at this point minus the pressure at this point. So it is P at some location S minus P at some location S plus dF times the area. So the area will be equal to, say, delta n. Let us say that the unit width, there is a unit width into the plane. So this times delta n. So what is it? It will be minus del P del S delta S times delta n. So this is the force in the S direction. What is the force due to gravity? The force due to gravity will be decomposed into the S direction and in the N direction. So let me extend the N direction like this. This is the direction of the velocity and this is the direction of the horizontal. This angle and this angle are the same. Alright. So the angle can be written as, so let us, before going into writing down the exact term for gravity, so mass times the acceleration of the object is equal to minus del P del S delta S delta N, and the force because of gravity is minus rho G, but it is acting in the Z direction, right? But the mass of the object is, rather the volume of the object is delta S delta N, and there will be another cosine of theta, right? There will be another, no, in this case, if this angle is theta, then this angle is also theta. Okay, so delta S times cos theta. Oh, rather it won't be cos theta, it will be sin theta. Because the projection of of this gravity force in the cos direction will be along the N direction, not the S direction. So the mass here will be rho times delta S times delta N times AS is equal to minus del P del S delta S delta N minus rho G delta S delta N times cos times sine of theta. Now the sine of theta will be equal to what? It will be equal to, so this particular height change divided by the, let me draw the element a bit clearly. Let this be the element, let this be the streamline direction, right? So we are bothered with this angle. So this angle is the same as this angle, and sine theta in this case will be equal to delta Z upon, hmm, what is the component of, still not clear. The acceleration due to gravity, how can we decompose the angle? Let's see. Mm, Okay, let us keep it like sine theta. Let us divide everything by delta S and delta N. So it becomes rho AS is equal to minus del P del S minus rho G sine of theta, where sine theta will be the rate of change of height of the streamline locally per increase in the streamwise coordinate. Okay, so sine theta in this case, it will be the rate of change of increase of height, or rather the increase of height per increment of the arc length. Okay, so it becomes rho as is equal to minus del p del s minus rho g del z del s. So this defines the Euler equation along the s direction. This this encapsulates how the streamline looks, nothing else. Essentially, the component of the gravity along, this is nothing but accounting for the component of gravity along the streamline direction, instantaneous streamline direction. Similarly, for the n direction balance, so momentum balance in the n direction, it will be, so what are the acceleration terms? The acceleration term as seen from the inertial frame will only be v square by r, where r is the local curvature with respect to which the fluid element is moving. Okay, so it will be minus rho delta s delta n, the mass of the element, times v square upon r. This will be the force acting in, this will be equal to the force acting in the n direction. So the force at this point will be P at n, the force at this point will be P at n plus delta n. So it will be minus del P del n delta n delta s minus rho g. So now the other direction will be del z del n. Instantaneously, let me just, okay, so instantaneously at this point, del z del n gives us the sine of this theta, whereas del z del s gives us the sine of this theta, that is how much z varies with an increment in s, but how much n varies, how much z varies with an increment in n, that will be equal to the cosine of this theta. It's simple geometry. Okay? So this particular thing is the cos of theta. So with this in mind, we can simplify this as rho v square upon r, where r is the local radius, is equal to del p del n plus rho g del z del n. So this is the Euler equation normal to the streamline. This is the Euler equation along the streamline. With the help of these equations, we can solve various problems of vorticity. I mean, you just need to find out all the various terms. Let us do a quick example. Let us consider a velocity field given by ax square I minus 2 axyj. So we have been given the velocity field in the Cartesian direction. Let us see whether this flow is divergence free. So del u del x is 2ax, del v del y is equal to minus 2ax. So when you add these two, you get 0. So the flow is divergence free. Now let us find out the acceleration component. So acceleration in the x direction is del u del x plus del u del t plus u del u del x plus v del u del y. This term is 0. So u is ax square, del u del x is 2ax, v is minus 2axy, del u del y is equal to 0. So this becomes 2a square x cube. Ay becomes u del v del x plus v del v del y. So this becomes ax square. So del v del x is minus 2ay plus v is minus 2axy del v del x, rather del v del y, which is minus 2ax. So this comes out to be minus 2a square x square y plus 4a square x square y. Let us in fact find everything out at the point x equal to 1 and y equal to 3. At x equal to 1, ax becomes 2a square and ay becomes equal to uh, y. So this becomes what? This becomes essentially this is 2a square x square y. So substitute y equal to 3. So this becomes 6a square. So the acceleration at this particular point at any time would be given by this. Now we need to decompose this acceleration. Now we have essentially ax and ay as two components of the acceleration vector, but we need to decompose it along the direction of the velocity. We need to decompose it along the direction of velocity. So how do you do that? Let us find out the unit vector along the velocity at this point. So the velocity at that particular point will be, so set a equal to 1, so it will be ai minus 6 aj. So the normal vector, rather the tangential vector, the s vector, it will be the u vector divided by the magnitude of the u vector. So it is ai minus 6aj divided by a times square root of 37. So the component of acceleration in the s direction will be the a vector dot es vector, essentially, which is 2a square I plus 6a square j dot ai. So the a cancels out, so the a cancels out, so it is I by square root 37 minus 6j upon square root 37. So this acceleration component along the s direction comes out to be 2a square by square root 37. So 6 minus 36 a square upon square root 37. How do you find the normal component of the velocity? So the normal component. So if I know the tangential component of the acceleration, right? The normal component can also be found out from the Cartesian component itself by taking a cross product of the tangential component of acceleration with the k vector, that is the vector facing coming out of the paper. So the normal component will be the normal component of as cross k. Actually it will be the minus of this, so it should be rather k cross, because if as is like this and k vector is pointing towards us, so k cross as will give us the normal component. So then you can find this out as well. So at a given point, you now know the as component and the an component of accelerations, right? Now, if someone asks that if the flow is, rather if the fluid element is moving along that streamline in the absence of any applied pressure gradient, what is the local radius of curvature of the flow? What is the local radius of curvature? So we make use of the fact that the normal acceleration times rho is equal to minus rho v square upon the local radius of curvature, and this is equal to, rather the rho we can cancel out, I don't know why I wrote this. So the normal component of acceleration equal to minus v square. So the velocity can be found out from here. The velocity magnitude is equal to square root of 37 times a in the es direction. So this is the magnitude and this is the unit vector along which, okay. So in that case, this becomes minus v square upon r. Anyway, I'm not gonna do the entire calculation because you have to find this out, find out this curl. Alright, so once you know as, you can take the curl, you can find out the v square upon r and find out eventually what r is going to be. Okay, so like this, one can calculate the different terms. Hmm, actually, the acceleration vector in the normal direction, would be the acceleration vector dot the normal vector in the n direction, and the normal unit vector in the n direction can be found out as a cross product of k cross es rather than the other way around. So this gives us the unit vector in the normal direction. Then you can take a dot product of the acceleration vector like we took the dot product over here. We can take this dot product and find out the normal component of an, subsequent to which we can find out the local acceleration component. Okay, so that's the way of doing it.